Hello, everyone, and welcome to another podcast or another episode of our podcast, The Data Science Decoded. I'm happy to say that Nir is back, and we're excited, and also Mike here with us. So, Nir, how are you doing? Um, and
Hey everyone. Hey Daniel. Hey Mike. I'm doing okay. Um, Still dealing with some personal challenges, but yeah, I think I'm back into orbit right now, and I'm very happy to be back and to see you guys.
Yeah,
same.
I'm really glad to see Nir coming back to us because he was really absent in the previous episode, and now we are full squad, and let's do something interesting.
Yeah, so the episode was the previous one about Turing, or the previous one. And yeah, it felt different, just two people doing that. And so, yeah, for sure, we're happy that you're back, and we wish you and your family and everyone best of everything. And today episode, we're gonna go over the one of the original papers of PCA, Principal Component Analysis, which is widely known and used in machine learning and data science today. And this paper is from 1935 by Harold Hotling, and the title is Analysis of a Complex of Statistical Variables into Principal Components. So already in the title, it says that. I did a little bit of reading about him. So he is a famous mathematician and statistician. Uh, been in various universities in the US, developed a lot of other important contribution also to economics um, on top of math and statistics. Also, it was written that after the World War II, he accepted a few refugees, Jews that ran away, including Avram Wald, that is famous if you've done A/B testing, and there's the wild criteria, etc., to decide when to stop experiments. So maybe we'll touch on his papers also in the future. So this
You
is a
mean
little bit
Wald? Daniel, you mean Wald?
Wald. Okay, I say Wald.
WALD, right?
Yeah. Okay, thanks for the
Uh,
correction.
Daniel, does the Hotelling has some formula or theorem or
Yeah,
lemma after
yeah,
his name? Because
yeah.
I don't remember.
There's a few at the Wikipedia page, so you can check. Um, so he's quite famous. And I said one of the two papers because there's another paper about PCA from 1908, I think, right near. You saw it.
I
Uh,
don't remember. I think it's even before that. I
oh,
think 1903 or something
oh,
like that.
yeah, crazy. So,
Maybe.
and I did saw that, but as far as I understood, the derivation that there wasn't like full, and this is more the official one that usually this paper usually has been cited if you talk about PCA. So we're gonna do this one, and let's dive into it. I have a
Daniel,
few questions for you. Yes.
Daniel, a very small remark we discussed before our podcast. It's very interesting that this paper and a couple of papers we
Mm.
discussed before was published in some psychology journal, right?
Mm. Yeah. Eugenics. We had a feature
Yes.
paper in eugenics
Yeah, yeah, yeah,
journal.
Yeah. Yeah, this paper was published in the Journal of Educational Psychology.
yeah.
And
Yeah.
by the way, he cites psychologists that did work with the correlation or independence of mental traits.
Mm-hmm.
And so this is very interesting paper in the sense that it's not conventional. He handling he cites I think Kelly's work, which is pure psychology, but he uses a lot of mathematics in psychology, which is I would say something that we lack today. It was very rigorous.
Yeah, rigorous. Yeah, I totally agree, and we touched upon that. And we'll see here, like some of the examples he gives later at the end are about like similar to SAT, psychometrics, when they have features about various
Mhm. Yes.
properties of intelligence. Um, cool. So I guess to your point, that's most of the data they had, and then they tackled
Yes.
that, right?
Hmm.
Okay, so I'll start. I'll add that there's a few chapters, and the first one is called Introduction. How surprising! And he says here, consider n variables attaching to each individual of a population. These statistical variables from x1 to xn might, for example, be scores made by school children in tests of speed and skill, in solving arithmetical problems, or in reading. We've touched upon that exactly. Or they might be various physical properties of telephone poles or the rates of exchange among various currencies. Okay, so he says it could be whatever measurements.
Hmm.
And he says the x's will ordinarily be correlated. So the features, right? So this is eventually features, as we say today, are
Hmm.
usually correlated. It is natural to ask whether some more fundamental set of independent variables exists, perhaps fewer in number than the axes that we did, which determine the values that those x's will take. And now he says if gamma 1, gamma 2, etc. are such variables, we shall then have a set of relations of the form, the features that we have, xi, for example, is then will be a function of those other variables that might exist.
Hmm.
So this is like a general form.
Daniel, a very small remark. I can see here the words correlated and independent in one paragraph.
Mm-hmm.
I want to emphasize that the absence of correlation and independence are two different concepts, and I want our readers to remember it.
So
Yeah.
give a few more words on that.
Yeah, because you know correlation is just some characteristics of the average of these random variables. Because how do we define uncorrelated how do we define uncorrelated variables? Uncorrelated variables has zero correlation. And what is correlation? Correlation is just the expectation of
Station.
x multiplied by y minus the average of x multiplied by average of y. And independence is totally different concept. It is the definition is that the density
Probability.
function of x and
Mm.
y in the case of continuous variables can be factored into the density of x multiplied by the density of y. And for example, for the Gaussian variables, these concepts are the same. But for the general variables, they can be uncorrelated but still be dependent.
Exactly. Yeah.
Perfect.
Yes. And he assumes Gaussianity all over this paper, by the way,
Yeah.
and that's why I think he probably more loose in terms of correlation and independence.
Yes.
Yeah, it says here, we shall consider only normally distributed systems of components having zero correlation and unit variances.
Yeah. Exactly.
Okay.
Hmm.
And there's assumption um, that let's see, it says here, if we use the symbol E to denote the expectation or mean value in the population of the quantity following it, the condition that the means shall be zero is expressed by the expectation of those gamma, right? So the new, uh, it's not factor, the components, right? The new variables that we're gonna look for,
Hmm.
we have
Yeah.
zero
He
expectation.
he calls it mental factors here
Yeah, yeah,
because it's
yeah. I jumped
technology.
about, yeah.
Yeah, these are random variables for me.
Or features. You know, You know, by the way, this zero expectation, we can take any feature and make and easily make it zero expectation, and it also can make any feature independently, totally independently of the other feature. We can make it easily having a unit variance. It is just scale and shift, and we are doing it, and we are standardizing. I don't remember what is the common name, standardizing or normalizing. Before we feed our variables into a neural net, for example, we normalize it. So we are making each feature having a zero expectation and unit variance. So
Yes.
please use it here.
And here it shows that mathematically that they're not correlated, those new gammas. It's showing that the expectation of gamma I and gamma j is the delta, the Kronecker delta function, right? It means it's zero everywhere except 1 when they have the same index.
Yeah.
Okay.
This is like saying the covariance or the autocorrelation matrix is the identity.
Exactly. Perfect. Then he says we're going to follow the notation of Kelly and express the x's, meaning our actual measurement, the features that we started with, in standard measures. So in a sense, they just normalize or standardize the data so that it will have zero mean and 1 standard deviation. Cool. Let's continue.
There is an interesting thing here. It is written here, we shall make use of tensor analysis convention, the repetition of the literal subscript. I thought that the tensor analysis was not known 90 years ago, but it was my mistake. And I think such notations today are called
Einstein notation, exactly.
or is it different notation?
No, it's exactly Einstein notations.
Yeah, okay.
Oh, really?
Yeah.
I didn't know that. So
In PyTorch, I think it is called very some command.
I know it if you do advanced courses in physics and you have to.
Okay.
Yeah.
I know it from Python. I learned it from Python actually.
Yeah. It took me a while to understand what he's saying here because, for example, equation number three is a matrix vector equation.
Yeah, they just miss the sigma. They just remove the sigma.
Yeah, they remove the sigma.
That's it. It's like I'm so lazy. I'm gonna write everything without the sigma, and I call it tensor analysis, Einstein notation.
But you know, guys, think about 19 years ago. You don't have computers.
No.
All this stuff printed on some printed machine. I'm not sure that the printed machine existed 90 years ago. But think about how do you print out summation sign, the summation sign.
The sigma,
Just think about it. So it is very intuitive that he decided to avoid it.
Yes, it is.
Cool. So now he says instead of x are features are some function of the gammas. He says now, okay, our z, because we normalize the data, is some linear combination. So he assumes here a linear combination of those gammas.
Hey, can you scroll up a bit? So for equation two, equation three, there is a duplicate. The first equation 3, he says, confining ourselves to the case in which the functions fi are linear. So that's where he basically says, okay, this generic function f will be linear in our case.
Yeah.
And so it's very important. And when you learn about PCA, they always tell you that PCA is a linear transformation, and this is why.
Perfect. Thank you for that point. So now we have our measurement z, right? We normalize it as a linear combination of those function gamma. And then he says here, let A, I think it's S, I'm not sure, denote the,
IJ, AIJ.
it's AIJ.
That's
Yes,
what
yes, it's
I
AJ.
understand. Yeah.
This is a cofactor of AJ.
Yeah, I didn't. So what is cofactor? I when I,
Cofactor,
I when I read it, I'm like, I have no idea what he's saying.
cofactor is when
Okay. Tell,
cofactor.
I'm not sure. What is it?
Okay, cofactor. Let's say an index IJ is when if you remember from a long time ago linear algebra when we learned about how to invert a matrix.
Yeah,
So you eliminate column I and row J.
Ah,
You calculate the determinant and you divide by the determinant of the original matrix, and that's element Ji of the inverted matrix.
when I studied in the university in Moscow, the name that they gave to it was something like a joint, maybe.
yeah, that's
Hmm.
what we studied also in the
Ah,
Technion. It was a joint.
Okay,
but it
so
was in Russian and it was in,
yeah, yeah. So equation 4 is basically saying what we know from PCA about the matrices that are unitary, right? So what he's saying here is that A transpose A is the
Equal to,
identity.
it
Is the
will
identity.
equals 1.
Yeah, is the identity matrix.
yes,
Yeah.
yes, 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 exactly.
And A transpose is also that's number 4.
Yes,
That's
Cool.
what he's saying here. Yeah.
So given that, now we can isolate the gammas, right? So we now can multiply both side by the
Uh,
inverse of
yes.
A, and we get that gamma k equals A jk times the z, our measurements.
yes. After the transformation, right?
Yes.
Yeah,
Which is a linear transformation.
perfect. And now he says, let our sk be the correlation between xi and xk, meaning our measurements, our features, sorry.
Mhm.
Um, and equal to unity, meaning he's gonna give some kind of constraint. And they're gonna be equal to unity if I equals k.
Mhm.
And at the end, he substitutes the zk and zi are measurements with what we established prior,
Mhm.
and we get that the correlation rsk is equal to the multiplication of asj with akj.
Mhm.
By the way, guys, why does the half of n multiplied by n plus one and not n multiplied by n minus one?
So I'll read it. It says the number of equations that we get is only what Mike said, half of n times n plus 1
Okay.
in parentheses. And why is that the case? I have no idea. I assumed he is right and correct.
Yeah, I also think he's right, but I want to understand why because here he's talking about
Yeah.
half.
Number of equations you have. Uh, you have and how many elements do we have? We have n squared elements in the matrix.
Yes.
That we
I
agree.
don't know. Yeah, I don't know. I need to think about it. Why it's n plus one. I
But
forgot.
the case he says here, it's underdetermined. He says that there's more
Yeah. Yes.
um, um, variables to find than equations.
Yes.
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 Yes. That's we know that about PCA because
Yeah,
of the rotations.
and in order how you solve it, you reduce the number of the variables, in a
Yes.
Yeah.
sense.
Yeah.
Um, okay, so he talks about it here.
Oh, the matrix is diagonal. Sorry, not diagonal. The matrix is
Triangular.
triangular.
Okay.
So or symmetric. Okay. So the low triangle equals the high triangle. That's why it's n plus one n.
Ah, it's like half.
Yeah. It's a correlation matrix. It's A
Yes,
multiplied
yes,
by
yes, yes.
A transpose. Yes.
Yes, the other equations are the same. So yeah,
Yes.
And
It
here
solves history.
he
yes,
says
yes.
here various modes of escape from the interden
Determinate.
indeterminates.
Indeterminate, whatever. Determinateness.
Yeah. So you have a. It's not in. Okay, I'll stop saying that.
Just give up.
Yeah. Um, so he says in the way to resolve the problem is to reduce the number of components,
Mhm,
which amounts to setting sum of the coefficients a as j equal to 0.
mhm,
If carried far enough, this results in fewer equations than unknowns, so the consistency conditions upon R as j may be obtained. Okay,
mhm.
so he says, okay, let's assume some are 0, and then we can solve this set of equations. And I want to jump because here he talks about something else about Spearman.
Mhm.
And
And here he mentions Kelly in Crossroads of the Mind of the Man.
yeah, a great name for a paper.
Yeah,
And let's see.
yeah. In this page is basically saying most of the we're interested in only the most powerful components because,
Hmm.
for example, he gives an example about linear regression here.
Yeah,
That
exactly.
we
That's what I want to read.
yes,
Um, in order to
he
get
said.
as far as may reasonably be possible in a given case in expressing the test scores xi, our data, in terms of a smaller number of components, an orderly procedure is required for selecting the components in the order of the definiteness of their existence or
Mhm,
of their importance for our purposes, and
mhm,
rejecting any which prove to be of little importance or
exactly.
which are not clearly defined by the data. An
Mhm,
analogous situation arises in fitting empirical curves, a series of the form y equals a plus bx plus cx squared, etc. So we do curve fitting. So here he said, oh, when you do deep learning. Um,
yeah,
just my joke that deep learning amounts to curve fitting.
it is.
Yeah, it is.
Everything amounts to curve fitting, you
Yeah,
know.
yeah,
It
yeah.
depends on the curve, but curves are sometimes very complicated and cumbersome. But still,
Yes, yes.
Um, so it says here, if the series is modified so as to consist of orthogonal functions, the successive coefficients have zero intercorrelations. Only
Mhm,
those terms should be retained which are significant.
mhm,
And then he says another analogy is the use of regression equations involving more and more variables from x1 to x whatever to explain or predict y, which is similar to the previous one, in my opinion.
yes, it's the same.
Uh, you do regression,
Mhm,
uh, and
it is interesting, by the way, this what he's writing about polynomials. I think if we replace this polynomial representation by the sum of orthogonal polynomials, for example, Chebyshev or Laguerre or
mhm,
Bernstein polynomials, it is interesting questions in terms of regularization. He's talking about here. This is one with which I'm not sure I fully understand. If this series is modified so as to consist of orthogonal function,
mhm.
the successive coefficients has zero correlation. I'm not
mhm.
sure I
Ah,
fully
you agree?
follow what is written here.
Yeah, I think is kind of hinting to the Karun and Loev how do you call it mm, Karun and Loev functions and basis. I think that
Okay.
he's hinting to that, which is very much like let's find an orthonormal basis, and now present our function as a sum of the orthonormal functions. I think it's called the decomposition of Karun and Loev.
Okay. So from a regular polynomial, you just turn it into sum of independence under some metrics. In order to talk about orthogonality, you need to define what is orthogonality, and in the function
Yes,
space, it is usually expressed by some integral. Okay.
yes,
Now I get it. Okay.
exactly, because the function space is kind of like a vector space, right? In a functional analysis. So
You
yes,
define operation properly, so it is just
yes,
a vector space. You have a
yes,
sum,
yes,
multiplication, distance. Yes.
yes, exactly. But I think that the first example here is one polynomial, and the second example is talking about multiple regression,
Yes.
like y equals ax1 plus bx2 and so on. That's the difference, Daniel.
Mm,
But it's the
okay.
same. It contributes after a while. It contributes nothing to the variance, and he hints about the analysis of variance here, right? ANOVA.
Yeah, exactly. And he says here, let's see, this analogy suggests that in choosing among the infinity of possible modes of resolutions of our variables into components, we begin with a component gamma 1, whose contribution to the variances of x1 as great as great a total as possible. That we next take a component gamma 2, independent of gamma 1, whose contribution to the residual variance is as great as possible, etc.
Mhm.
This we shall call the method of principal components. Its
Yes.
technique will be considered in the subsequent sections.
Now I have to say something here. An
Mhm.
anecdote.
Yeah.
Who taught me this? Do you know? Mike taught me this.
Okay.
Mike taught me this
Miami?
in the OFDM communication course in the method of eigenbeamforming.
Yeah.
That
Wow,
you
wow,
yes,
wow.
that you beamform the beam into the direction of the maximum eigenvalue,
Yes, yes,
which
yes.
is exactly the maximum component here.
Wow, I had no idea about this.
How it happened that you remember it and I don't remember? Now after you reminded me, I think I recalled it from my memory, but I almost forgot it. It was like
Yeah,
in my previous life, because I'm not working in this industry for 13 years.
yeah. I work with these methods of beamforming, eigenbeamforming, eigendecomposition in radar all the time. That's why I remember it.
Interesting, interesting.
Yeah.
By the way, there is interesting connection, at least in my brain, of the maximal variance direction and the information.
Oh
Yeah.
yeah, yeah.
Yes, because I'm not sure he's talking about it in this paper. Maybe he is, but and they missed it. But the direction of the maximal variance. What does it actually mean? What is the
Mm-hmm.
maximum variance? Maximum variability. So we have, in some sense, I don't have a clear explanation. Maybe you guys have, but for me it's just the direction of the
With
maximal
information.
variance. And then you are looking for the second direction, which is orthogonal to this, but this is the second maximal information direction.
Mhm.
So
Exactly
for me,
right.
it's very
In,
natural.
in an information, in a Shannon information theoretic sense.
Yes, yes,
Yes, yeah. But I don't think he is talking about it. I think it's before Shannon.
It's
This,
before, yeah.
yes.
yeah,
Yeah, but in my mind, also reading this, I'm thinking it's talking about also always looking at the highest variance. So I also
yes,
say, okay, it has the most information. That's why it's interesting.
Yeah,
yep,
yeah.
yep.
Um,
And by
and
the way, when Mike taught me this, he derived it exactly like him.
Yes.
Yeah, what's the uh, optimization problem here? Let's maximize the variance constrained by a
Yes.
unity or orthogonal, or sorry, orthonormal, a normal volume for the vector, and that's it.
Yes.
And
Do you
you get
know, Nir, do you know who taught me this stuff? Do you inform
no
me?
one Esri.
Yes, yes, Dr. Donald, yes, yes.
Yeah,
I think so. I think so. I think we need to invite him because he's a really sharp guy.
yeah, the one Esri. Yeah,
One of the best. I can call him. He's some kind of mathematician. He's very one of the best mathematician. One of the most talented and most sharp
yeah,
engineers and mathematicians I met in my
yeah,
20 years career in Iterative. So I think
yeah.
if we are going to invite
Mm.
anybody, he's one of the best candidates.
100%, 100%. He, by the way, he and I served in the same unit.
Ah,
Uh,
really? Okay.
yeah, and also he's one of my mentors, I would
Yeah.
say. Yeah,
By the way, he was my mentor too.
yeah, I know. In a
Yes, yes, because I arrived with zero knowledge in signal processing. I had only PhD in math. No, for me, I remember it. Fourier transform was some multiplication of some orthogonal matrix. And he in several months just converted me into some kind of low level engineer with some good understanding of the math. You know,
yes,
so every one of us has mentor.
yes, for sure.
Cool. So maybe it's foreshadowing for the future when we'll start maybe do some talks with other practitioners.
Yes, guest
Uh,
episode.
yeah, for sure.
Yes, yes.
So I'm not going to read this whole page, but so we get back, so we have time to other things. But I'll say, he says here the usual story that people say, like if you have a spread of data, so PCA is like trying to fit ellipsoids, right? So if the data is somehow spread in this direction, so you take the ellipsoid and fit it to this direction of the
Mhm.
data and etc. So he has like a geometric point of
Interpretation.
view. That's why he
Yeah.
calls it. So let's continue. Um,
You know how we call this process in electrical engineering? We call it decorrelation.
Mhm. This seems reasonable. Yeah.
do you mean PCA or which process?
The PCA process, the
See,
Ah,
decorrelation. Yes,
I
it
didn't know that.
it will it will take the matrix and will make a diagonal out of it, but in the diagonal there will be these variances, right? So it's not the same variance, so it's not white, but it's decorrelated.
yes.
Mm.
By the
Oh,
way, guys, we have 15 minutes. I just have here. It was written by the Google Meet. We have 50 minutes.
Yeah.
15 minutes.
left.
Yes, I also
Yes.
have this.
Oh, yeah, because I started it earlier.
Mm,
Okay.
Okay, so when it stops, we start another one and then we'll take care of that.
Yes. Okay.
okay.
Cool. So chapter number 2, and again we have like 6, 7, so we need to speed up. It says derivation of the method, and then he says here squaring each side of those master equation, we get each um, coefficient squared, and he
Mhm,
sums them all up.
mhm,
And he says, and that the first term is correctly described as the contribution of gamma 1 to the variance of z1.
mhm,
And then he says the sum of the contributions of gamma 1 to the variances of all the z's is um, called S, capital S, and it's equal to A11 squared plus A21 squared, etc.
Yes.
mhm.
So it's like it's taking one row, not one column in the matrix.
Yes.
Yeah.
One column.
Yes.
Cool. And then he
Oh,
says here, okay, we need to remember the constraint that we
mhm,
have the multiplication of those coefficients is equal to the correlation.
mhm.
And then he uses the Lagrange
Multipliers.
multipliers. Yeah, he says it here. So because we have an optimization problem with a constraint,
Mhm,
and then he solves it, and he gets set of linear equations.
mhm. Yeah, he basically solved the optimization problem, and he gets that it's that's the eigen decomposition
Yes,
basically. This is exactly what Mike derived on the whiteboard. I don't
yes,
know, 20 years ago.
yes. 15.
15?
Okay.
Okay.
15, maybe 18. Okay.
Yeah.
Something like that, many years ago.
Yeah. Yeah.
I won't go here in depth unless you think something here is important because there's
No,
some normalizations. I'm not sure.
no, it's the usual eigen equations.
Yeah, it's just derivation of the maximal eigenvalue and the maximal eigenvector corresponding to this maximal eigenvalue. There's some math you need to do, some, I call it technical debt you need to do to get all this beautiful stuff like PCA.
Yeah.
Okay.
Can you scroll up a bit?
Yeah.
So is in the last sentence the problem of finding component gamma one, which will account for as large as possible part of the total variance, it does solve by finding, and then that's it.
Yes,
The largest root of the characteristic equation 18, which is the characteristic equation is the eigen equation. So
yes.
that's the usual PCA or SVD or whatever you want to call it that we know from modern linear algebra.
Yeah, linear algebra.
Yeah.
By the way, I don't remember that this eigenvector of this direction of any other direction should be of norm one, should be unit norm, or it is not
Yes.
necessarily
Yes.
have.
It's,
Yeah,
yes. It's an orthonormal basis. Yeah.
okay.
Yeah. The scaling are in the diagonal matrix of the SVD.
Hmm.
Yeah.
Yeah.
Okay, let's
By the
continue.
way, he's talking about this here. Can you scroll up a bit? Stop here. Last paragraph. The orthogonality among principal components, which we have populated for multiple roots, holds for simple roots. So yes, there is orthogonality between the principal components, which are the what we call the principal vectors. Okay.
But orthogonality, yes, but
But yeah, the question if they're normalized, but
Yeah. It's also normalized. Yeah. Yeah. In his case, it's the he requires that the norm will be the correlation, right? That's his but it's the same as saying the norm is one, and let's find the eigen value that will scale it.
yeah. Because for any eigenvector, if you multiply it for some by some constant number, it will remain eigenvector. So
Yeah,
you need some normalization, and then usually
exactly.
it's the unit normalization.
Exactly. Yeah, it doesn't really matter. Right? You're right.
and now he goes to the third chapter, which is called geometrical meaning.
Hmm.
And here he derives, as far as I thought, this is what I remember is as the way to do it. So how this method is different than the one previously. Previously, it was more optimization. And here he actually says, okay, we have this some kind of ellipsoids.
Hmm. Exactly.
But
This is
then
this is Malanobis, by the way. 23 is Malanobis.
I have no idea what's Malanobis, but cool.
Yes, yes.
Yeah, it's the term inside the Gaussian, the multivariate Gaussian.
Yeah.
X transpose r to the minus 1 x.
Yes.
This distance, this scalar.
Okay. I my math courses are probably not as advanced as yours, but that's why you're here.
Yeah. Malonobis actually distance just neutralizes correlations and different scales or different units. This is solely designation.
So tell me what's the difference of this derivation to the previous one?
It's not a derivation, it's an interpretation, Daniel.
Yes.
Ah,
It's the geometrical meaning of the derivation. And he's saying we have a hyperellipsoid in both direction, and the principal components or principal vectors will be in the same direction of the principal axis of the ellipsoids.
Yes.
If you're talking about
mm.
ellipsoid in the meaning of the Gaussian term.
Here I like I understood this. This is an ellipsoid. Okay.
Ellipsoid. Yeah. That's also Mahalanobis in another way, in another manner. That's a diagonal matrix here. Right?
Okay. Let's
By the
continue.
way, it is interesting to compare this PCA stuff with the Grand-Schmidt orthogonalization. Because
Yes.
in the Grand-Schmidt orthogonalization, you are just finding a linear transformations
Yeah.
of the axes which orthogonals. It is a difficult word. Which makes your vector which actually builds an axis in which your set of vectors are orthogonal. But it is very important to emphasize that in Gram-Schmidt you are not talking about variances. You are just normalized in some way, and I'm not sure. It is not necessarily that the first vector will be the vector of the maximal variance of the maximal
No,
information. You are just
no, it's not.
normalizing it, and
Yes.
and
Yes.
interesting.
By the way, you remember another here in the iterative solution. If we get to that,
Yeah, chapter 4.
yeah, in the iterative solution, he's basically saying, okay, we find the first principal component, and then we project onto this first principal component and take it out, like minus, okay, or subtract it, and then we do it again. That's the
Yeah.
iteration.
Yeah.
Okay? And that's very resembling to the Gram-Schmidt, except what you said, that Gram-Schmidt does not forces any constraint on
Yes.
the variance, but also uh, uh, you know what it reminds me? It reminds me of again something you taught me, Mike, in the same course, the successive interference constellation method.
Yeah.
And you take the most the direction of the most power, and you take it out of the matrix, and then you do it again and again, and you cancel
Interesting.
the directional interferences like that.
Yeah. And do you want to hear what it reminds me?
Okay.
Much more simpler thing. Do you remember
Mhm.
what is Gauss elimination for the
Yes.
linear system for solving linear system of equations? The same idea. So the math is driven in many cases by the same idea but different implementations.
Yes. Yes.
Interesting. Okay, so this is the iterative
Mm-hmm.
method
Yep.
to get the
The
PCA.
order of eigenvalues. Yeah.
Yeah. Okay, so maybe we can get to there's an example.
Mm-hmm.
So this is the example with the grades of children, 140 children, and we can see the correlations for reading, speed. So this is like the features X.
Mm-hmm.
Reading speed, reading power, arithmetic speed, and arithmetic power. Okay, and then he gives us example, given the correlation matrix, how can we do the iterative method. So he starts with some guess,
Mm-hmm.
and then does it iteratively until the error, like the differences are really small.
Mm-hmm.
That's as far as I can understand.
Yeah, that's what he does. By the way, we're not doing that these days like that. We're doing SVD or
Mm-hmm.
QR decomposition and stuff like that.
Yes.
It's more elegant and it gives you but it's not the same method, but it's the same result.
Yeah.
And there's a chapter now in chapter 6. It's about sampling errors.
Mm-hmm.
So that was interesting because yes, okay, you got those principal components. How can you be statistically uh, confident? So is this difference between them statistically significant? That's like the question he starts with, and then he uses some tools, probably Fisher somewhere is there.
Yeah, Fisher transformation. Yeah.
Yeah, to calculate given data
Mm-hmm.
or results if they are statistically significant.
Yeah.
Because maybe like two principal components are really close to each other, and then maybe it's due to noise, etc.
Yeah. I think that this is a part of what we call now. He is calling it error, but sometimes the interconnectedness between or intermodulation between the features are not
Mm-hmm.
linear, and then PCA will not give you
Mm-hmm.
a optimal results.
True.
Right. Yeah, and you will see it in the errors, obviously, if you.
Yeah, today you have like a kernel PCA for that case, right?
Yeah.
First you
Mhm.
transform it with kernels to some another
Yeah,
space when it is linear there, and then you do regular PCA.
yeah.
Yes. Yes.
Okay, let's see. It jumps between pages.
Did you guys? I'm very interested to hear about your usage of PCA in
Yeah,
data science, Daniel.
yeah.
And
So that's what I wanted to talk at the end. I
mhm.
think we're kind of done because it does a lot of analysis of the errors and stuff,
Yeah,
which
yeah,
is
yeah.
less interesting. And he says at the end he's going to continue in October issue. Cool.
By the way, you were
Yeah.
talking about kernel PCA, and then I'm talking when I'm interviewing data scientists. I always ask, what is the problem with kernel PCA? And surprisingly, many of them can tell very simple things because now you have some features, and these features are meaningful. You know what these features actually describe and depict, and then you are doing some esoteric transformation, some kernel, some sine or cosine, or just you just know x in the power of 3. Do you know what you're getting? You are getting linear features, but what other features? Nobody understands it. So it is actually good, but there is some very big problem about it because then you get some features. These features are meaningful. These features characterizes something, some process, some procedure, something that you understand, and then you apply
Kernel
some
PCA.
transformation. Not because linear transformation is okay. You understand what it does, but non-linear transformation, for example, some sine or cosine, some radial kernel, or something like that, some polynomial kernel. You don't know what you get. You don't know which units you are getting. You don't know what these new kernelized feature describe, and in the industry is a very big problem. For example, in one of my in my previous company, uh, I managed to find some very clever and not very complicated transformation to make our features much more convenient. Not just zero correlation and linear related, but still I managed to transform it in some new form, and then I showed these features to our analyst or security analyst, and told me, okay, now you have a very good model, but you need to explain how on which grounds do we decide which attack is malicious and which attack is not malicious, and what they're gonna tell us CISO. Yeah, I managed to build some very good features, but the transformation is very complicated. Okay, in the industry, if you want to publish some paper, it is okay. But if you're working in the industry, explainability
Yeah.
avoids you from such stuff. So use kernel PCA, but use kernels you understand.
Yeah.
Interesting.
Mike, question: how do you decide if a set of features are linear or not?
In this case, and it was not just about linearity. Actually, what I found the transformations. I found the transformations for which I was able to fit very simple linear regression with very small test error. So it is, I don't know how it is called. It is called generalized linear regression or kernelized. I don't remember the terminology, but in this case, I kernelized my features. I transformed my features in the way which a relation between the output and by the way, I did nothing for the output. I did only for the input, but I managed to find some transformation which was very good, which enabled me to fit in a very precise way some linear regression, very simple integration. With most of the coefficients were zero because I used some regularization, but it was as far as you can think of the explainability. I couldn't explain what did I get. Okay,
Yeah.
and this.
So my question is then, if the problem explainability, so how do you explain a neural network? Like it's also nonlinear.
Yeah, we don't explain. Here for this specific problem, we used some tree-based approach.
Yeah, that's more explainable.
Yeah, in this trees approach, we use something like it is called Shapley values,
Mm-hmm.
and we also use some Lime linear. So if you are using trees or random forest or even some simple XGBoost, you quite
Like the trees behind you.
yeah, and you can kind of explain it,
I
okay?
agree.
But for neural nets you have similar methods. You have Lime. I think Lime originally was developed for neural networks. By the way, now it is a very intensive and very interesting research about the explainability of LLMs. And I'm going to record a podcast in a couple of days. It is going to be in Hebrew, but about mechanistic interpretability of LLMs.
Mm.
The interpretability, it is not exactly explainability, but there's quite close terms, so you can't really explain stuff in neural nets. But in my case, if when I use the original features, I have some good explanations because my features were explainable, and after my transformation, I lost this explainability. So use kernel PCA, but be careful in the explainability domain.
Yeah. I would add that in my practice, I did use PCA. And maybe it was actually kernel PCA, but the motivation was a dimensionality reduction, right? So coupled with why do I want to reduce dimensionality? I want to avoid overfitting
Yeah.
in a sense, right?
Okay.
So let's say I start with a lot of features. Most models overfit easily. Now I'll reduce the dimension.
Yeah, I
And
use it for the same purpose because I
and
have
still
yeah,
have the same information or most of it still there. Actually, if I lose some information, maybe it's good again. It
yes.
prevents over. It's like a regularization, right? Method
Yeah.
to my problem, and then I use whatever I needed on the output of those features. So yeah, probably similar to your use case.
I think when your features are very noisy, PCA can help you in filtering such very noisy features, or maybe it will incorporate this noisy features, the coefficients, which kind of kill most of the noise that exists in these features. I think it was the case
Yeah.
for my transformation, which I found.
Mhm.
But if you are using if you are using PCA, it's not a problem because you can easily explain it. But
Mhm.
kernel, not always.
Perfect. So thank you for this episode, and happy that again Neil was back, and it's the three of us. And see you everyone on the next episode.
Thank you very much. Bye bye,
Bye.
guys. Bye.